Bismillah ar-Rahman ar-Rahim. Assalamu alaikum everybody. In the next presentations we are going to talk about the general principles of pharmacodynamics, which is the core of pharmacology. As you know, pharmacodynamics deals with what the drug does to the body in terms of action and their mechanisms. I'm going to give you a general plan of what we're going to discuss in pharmacodynamics. First, we'll talk about sites of drug action, where drug acts, 4 different major sites of drug action, including ion channels, pumps, enzymes, and receptors. We are going to talk about receptors in detail in terms of types, what are the different types of receptors. We are going to talk as well about the different ligands that bind to the receptor and how the receptor activity is regulated. The second part, we'll talk about the different types of drug responses, including graded response and quantum response. We'll end up pharmacodynamics and talking what will happen in drug-drug interaction if I take more than one drug at the same time in terms of antagonism or potentiation or synergism. So today's lecture we are going to concentrate on where drug acts, what are the sites of drug action. We are going to speak in details about receptors, what are different types of receptors, and we speak specifically today about receptors linked to ion channels. So what are the different types, different sites of drug action, where drug acts in the body? Maybe the first major site of drug action which we list are ion channels. Ion channels. Drugs, they can either block or activate ion channels. Maybe the most famous examples are the calcium channel blockers. Calcium channel blockers. These drugs, they have very important clinical use in treatment of different cardiovascular diseases, including angina pectoris, hypertension, and arrhythmia. Maybe the most famous example of calcium channel blocker is nifedipine. Of course, we are going to speak about this class of drugs in details when we talk about drugs used in treatment of cardiovascular diseases. The second site of drug action are the pumps. And maybe the most famous example of drugs which acts on the pump is omeprazole, which is a proton pump inhibitor. It inhibits the proton pump and therefore decreases gastric secretion. A third site of action of drugs are the cell enzymes. And maybe the most famous example is aspirin. Aspirin is very known analgesic, which is used for treatment of different types of pain and inflammation. Aspirin acts by inhibiting cyclooxygenase enzyme. We'll speak in details about aspirin when we speak about drugs which are used in treatment of pain. The fourth major site of action of drugs are the receptors. So we are going to speak in a little details about receptors, what are they, and how they are involved in drug action. First, we have to know what we mean by a receptor. What is a receptor? What is a receptor? Usually, a receptor, they are protein macromolecules which are either present on the plasma membrane or floating in the cytoplasm, or they are present in the nucleus. The most famous are the plasma membrane receptors, which are present on the plasma membrane of cells. Usually, receptors, they have different binding sites. This binding site will allow certain drugs to bind to these receptors. Okay? Now, there are generally two different binding sites. One binding site is known as orthosteric binding site. The other binding site is known as allosteric binding site. There is a difference between these two binding sites. Usually, orthosteric binding site, when an agonist binds to this binding site, this usually results in a response, a physiological response. While allosteric binding sites in general, they don't produce a response, as we will say in a few minutes. Okay? So generally, there are two binding sites on a receptor, orthosteric binding site and allosteric binding site. So what will bind to the orthosteric binding site? What will bind to the orthosteric binding site? Orthosteric drugs, they are either agonist or antagonist. Therefore, orthosteric drugs which bind to the orthosteric binding site, they act as an agonist or they act as an antagonist. What is the difference between these two? I will say in a few minutes. So both of them, an agonist and the antagonist, they have the ability to bind to the receptor. They have the ability to bind to the receptor. عندهم القابلية للاتحاد مع هذا المستقبل. This is known as an affinity. Affinity. Therefore, affinity, what does it mean? The ability to bind to the receptor. Therefore, both agonist and antagonist, they have affinity, ability to bind to the orthosteric binding site. Okay? Now, once an agonist binds to the orthosteric binding site, it will change the conformation of the receptor in a way that will result in a response. Therefore, an agonist, once it binds to the receptor, it produces response. This is known as intrinsic activity. Therefore, intrinsic activity means an ability to produce an action. Agonists, they have intrinsic activity. They can bind to the receptor. They can change the configuration of the receptor in a way that ends up with a response. Okay? Antagonist is the contrary. It does not have intrinsic activity. That means it does not produce an action. That's why it is known an antagonist. Antagonist does not produce an action. So what the antagonists do, it sits in the receptor and prevents the access of the agonist to the receptor, i.e. it prevents the action of the agonist. Therefore, an antagonist prevents the action of the agonist. Antagonist in Arabic means ضاد. تضاد تأثير الشاذ, an agonist. Okay? Now, so an agonist can produce an action? Yes. Antagonist can produce an action? No. Okay? Now, last property, the agonists, they have efficacy, as we will say later, inshallah, next or the third lecture about pharmacodynamic, efficacy. Efficacy usually of the agonist above 0 up to 1. Okay, therefore, agonists, they have efficacy, ability to produce certain response, efficacy. While the antagonist, it has no efficacy. Efficacy is 0. Okay? This is the orthosteric agonist, orthosteric drugs. They might be as an agonist with affinity, intrinsic activity, and an action and efficacy, while the antagonists, they have affinity, but they have no intrinsic activity and they have no efficacy. This is the first drugs which binds to the orthosteric sites, and usually binding of an agonist to the orthosteric sites will end up in a response. A second site are the allosteric binding site. The allosteric binding site usually, as we have said, once the agonist bind to this receptor, usually, but sometimes some drugs they can produce very little, but usually they don't produce action on their responses. So what they do, the allosteric drugs, what they do? Once they bind to the receptor, allosteric agonist, one that binds to the receptor, it might increase the affinity of the orthosteric agonist, the affinity of the orthosteric agonist to the receptor, or increase efficacy of the orthosteric agonist. Increase the efficacy of orthosteric agonist, okay? This is first. Therefore, allosteric drug, what does it do? Increase either affinity or intrinsic activity or efficacy of the orthosteric agonist. So what will happen? In this case, increase in the response of the orthosteric agonist, okay? This is known as positive allosteric modulators, or BAM, positive allosteric modulators. Therefore, positive allosteric modulators, what they do, they have no effect on their own, but once they bind to the receptor macromolecule, they either increase the affinity or the efficacy of the orthosteric agonist. These are positive allosteric modulators. Maybe the most famous examples are the benzodiazepines, which act as a positive allosteric modulators on GABAA receptor. Okay? Other type of allosteric modulators, there are drugs which, when they bind to the allosteric binding site, they decrease affinity of the agonist to the receptor, and they decrease the efficacy as well. Okay? Therefore, second group, they decrease the affinity, the ability of the orthosteric agonist to bind to the receptor is decreased, and as well the efficacy is decreased. That means what will happen to the action of the agonist, orthosteric agonist? The action will be reduced. The action will be reduced. These drugs, they are known as negative allosteric modulators. Negative allosteric modulators, okay? Or NAM. Usually, they have very little application. Most famous are the beta carbolines, which act on the GABAA receptors. Okay? Therefore, positive allosteric agonists or positive allosteric modulators, they are now a new group of drugs which are introduced into medicine, especially for treatment of many behavioral and central nervous system diseases like Alzheimer's disease. They say that this group of drugs, they can produce physiological response with very little toxicity, as we will speak when we speak about the groups of drugs. Okay? So these are the receptors and how they are stimulated by different types of agonists. So what are the different types of receptors in the body? What are the different types of receptor in the body? Of course, the body contains hundreds types of receptor, but all of them, they belong to three major families. All the receptors in the body, they belong to three major families. The first family is known the ion channel linked receptor. Ion channel linked receptor. This is the first group which we'll talk about, inshallah, today. The second, they are known as G protein linked receptor. G protein linked receptor and the membrane enzyme linked receptor. These two groups, inshallah, we'll talk about them next presentation. Okay? Now, today we'll talk about the first group, the first family of receptors in the body, which are receptors that are linked to ion channels. Okay. So how these receptors, the ions channel linked receptor or receptor linked to ion channels, how they look like? What is their major structure? Usually they are formed, as you can see here, they are formed from 5 protein molecules. They are formed in a way that they surround what's known as an ion channel. Conformation of the receptor is made in a way that in the middle there is a channel for ions. Okay. So these receptors, ion channel linked receptors, they are known as pentameric receptors. Why pentameric? Because they are formed from five proteins, maybe 2 similar, 3 different proteins, 5 proteins. Therefore, they are known as pentameric receptors. There is tetrameric receptors as well, and trimeric. Tetrameric means the receptor is formed from 4 protein structure, or trimeric formed from 3. But the most famous are the pentameric, which are formed from 5 protein structures surrounding ion channel. That's why they are known also as ionotropic receptor. Why ionotropic receptor? Because when they are stimulated, they lead to opening of certain ion channels. That's why they are known ionotropic receptor. Okay. These receptors, they are stimulated by agonists. They have a specific site for binding of an agonist. That's why they are also known as ligand-gated ion channels. Because, as you know from physiology, there are other types of ion channels which are opened by changing membrane polarity, which are known as voltage-gated ion channel. These are ligand-gated ion channels. Okay. Therefore, ion channels linked to receptors, they are also known as pentameric receptors. Okay, because they are formed from 5 protein subunits. They surround an ion channel. Therefore, they are known as ionotropic receptor, and they have a site for binding of an agonist binding site. Therefore, they are known as well as ligand-gated ion channel. Okay. So now these receptors, when they are at rest, of course, as you know, they are present on all excitable membrane, like neurons, like skeletal muscle, like smooth muscle, anyway. Therefore, when the receptor is at rest, when the agonist is not binding to the receptor, in this case, the ion channels are closed. The ion channels or gate, the gate to ion channels are closed. You have the closed ion channel. In this case, the biological membrane is said to be in polarized state. Polarized, why? Because sodium is concentrated outside and potassium is concentrated inside, and this will create a negativity inside the membrane, and the membrane is said to be polarized. If you just imagine, this is the extracellular space and this is the intracellular space, So potassium is concentrated inside the cell, sodium concentrated outside the cell. This will create the negativity of the membrane, and the membrane is said to be polarized. Okay. Now, once the agonist bind to the receptor, it will change the configuration of the protein of the receptor, change the configuration, it gives away, it opens the channels, it opens the channels, it opens the channels, okay? Now, once an agonist binds to the receptor, it opens the channel. When it opens the channel, it means ions will rush in or out. It depends on the concentration gradient of the ion and type of receptor. Rush in or out, okay? Once the ions rush in or out, that means will change membrane excitability, will change membrane excitability. Excitability. It depends on the type of ion which enters or exits. Excitability. Okay? Okay. Now, so what will happen the excitability? Either two things. There is no other third alternative. Either two things. Either membrane becomes more excitable, membrane becomes excitable, or sorry, we can say excitable, not more. More excitable means excitation, or the membrane becomes inhibited. Inhibition. Okay? Therefore, when the agonist binds to the receptor, it will open the channel, certain channel. Channel means rush in or out of certain ions. This will change membrane excitability. Either membrane becomes more excitable or less excitable, means inhibition. Okay? So we'll talk first about how, I'll take example of a membrane excitation by ion channel linked receptor and membrane inhibition by ion channel linked receptor. Of course, we will talk about the most famous examples. So the first most famous example we are going to discuss are the acetylcholine nicotinic receptor. Nicotinic receptor of acetylcholine. As we know, nicotinic receptor, they are present in different sites in the body. Nicotinic receptor, they are present in neurons, at the neurons on CNS. They are present in the ganglia of the autonomic ganglia. They are present on neuromuscular junction of the skeletal muscle. Okay? So the receptor are nicotinic receptor, which are present in different places in the body, and the agonist is acetylcholine. And the agonist is acetylcholine. Acetylcholine is the agonist. So what will happen? What will happen? At rest, we have said the membrane is polarized state. Okay? Polarized, we have explained, that means the membrane from inside is negatively charged because of the concentration of potassium inside and sodium outside, and the membrane is polarized state, in polarized state. Okay? Now, once acetyl, this is the rest state. This is the rest. Rest means that the ion channel are closed. The ion channel closed does not permit entrance of sodium. Once the acetylcholine binds to the receptor, as you can see here, the acetylcholine, once it binds to the receptor, it will change the configuration of the nicotinic receptor, opening sodium channel. Opening sodium channel. So what will happen? We know that sodium is concentrated outside. It will rush into the cell. It will rush into the cell. So sodium will enter the cell. Will enter the cell. Rush into the cell, into the cytoplasm. So what will happen? It will reverse polarity. It will reverse polarity. So inside becomes positively charged and outside becomes negatively charged. Reversal polarity. This is known as depolarization. depolarization. يبدأ في البداية كان الممبرين، كان الغشاء كان في حالة تأين، وبعدين حصل له إزالة التأين depolarization reversal of polarity depolarization always in pharmacology it is an excitation. What does it mean, excitation? What does it mean? Means if it is in a neuron, the excitation will travel through the neuronal axis or axon, okay, to the neighboring neuron, and the activity will spread from one side to another. If it is happens in ganglia, that means the excitation will be traveled to the postganglionic nerve fiber. If it is a neuromuscular junction, for example, it will depolarize the motor end plate, and this depolarization will trigger the contraction excitation contraction coupling, and will end up with muscle contraction. Okay, this is one example. There are many examples which we will take during our study of different groups of drugs, but this is the most famous examples. Therefore, example of ion-linked receptors are the nicotinic receptor, and the agonist is acetylcholine. And the receptors, they are nicotinic receptor, which are present in neuron, ganglia, or neuromuscular junction. At rest, when the receptor is at rest, the membrane is in polarized state, sodium outside and potassium inside. Once the agonist acetylcholine binds to the receptor, it will produce change of conformation of the receptor in a way that it will open sodium channel, sodium will rush in, causing depolarization. Depolarization means excitation, muscle contraction, neuronal excitability, etc. Okay? This is first possibility of membrane excitability. The second possibility is membrane inhibition. And I have given you the most famous example. First famous example is the GABA receptor, GABAA receptor, which are ion channel linked receptor. What is GABA? GABA actually it is a central neurotransmitter known as gamma amino butyric acid. It is abbreviated by GABA, gamma amino butyric acid, abbreviated by GABA. GABA as a neurotransmitter, it acts on two different types of receptors, as we will take inshallah later when we talk about CNS drugs, GABAA and GABAB receptors. GABAA, they are linked to ion channel. GABAB, they are linked to G protein, as we will discuss later. Okay? Now, GABAA receptors at rest, as we have said, chloride is concentrated outside, and potassium, of course, chloride and sodium as well outside, and potassium inside. So what will happen? At rest, membrane is polarized. State. Once GABA binds to the orthosteric binding site, this is the orthosteric binding site. GABAA receptors is a very good example of receptor with orthosteric binding site and allosteric binding site. Once GABA, which is the orthosteric agonist, bind to its receptor, it will open chloride channel. Chloride will rush in because chloride is concentrated outside the cell. So what will happen to the chloride? Chloride will rush into the cytoplasm. Of course, chloride is negatively charged. That means it makes the inside more negative, more negative. It was polarized. So what will happen after rushing of chloride? Becomes hyperpolarized. Hyperpolarization. Hyperpolarization. Okay? It was polarized, and by entry of chloride, which is negatively charged ions, the membrane becomes hyperpolarized. Hyperpolarization. Hyperpolarization means the membrane becomes less excitable. Less excitable. If it is less excitable, means that inhibition. Less excitable needs a stronger stimuli to produce an excitation. Therefore, it is inhibited. That is inhibition. Inhibition. Okay? Then, I repeat, GABA is a pentameric receptor, GABAA receptor. This pentameric receptor linked to chloride channel. At rest, the channels are closed. When GABA binds to the GABAA receptor, what happens? It opens chloride channel. Chloride will rush into the cytoplasm. Rushing of the chloride يدخل داخل الخلية. Rushing into the chloride into the cytoplasm will increase the polarity. This is known as hyperpolarization. Hyperpolarization means the membrane becomes more negatively charged. That means it needs a stronger stimuli to be excited again. So therefore, this is an inhibition. Okay? Okay? Now, this is GABA is very famous example of pentameric receptor, which act as allosteric binding site for GABA, orthosteric binding site for GABA, and allosteric binding site for benzodiazepines. So benzodiazepines here, they act as allosteric agonist. Positive allosteric agonists, which we call them BAM. Therefore, benzodiazepine, what does it do in this case? It opens the receptor. It increases the frequency of chloride channel. Increases the frequency of opening of chloride channel. That's why it potentiates effect of GABA on the orthosteric receptor. Okay? So these are the two possibilities which can take place due to change in the excitability of the membrane by opening of ion channels. Okay? So what are the properties of ion channel linked receptor? What are the general properties? First, they produce very fast action. What does it mean, fast action? Action takes place in a fraction of millisecond. You cannot imagine the speed of the action that takes place. That's why these kind of mechanisms are used by the nervous system in general. Nervous system, like sensory, like motor activity, like behavioral سلوك. كلها takes place very fast. Just you think if you want to walk, you can walk. Yeah. The moment that you decide to walk, you can walk. The moment you decide to move your hand, you will move your hand. It is very fast in terms of sensory or motor or behavioral. Okay? So it is used by the nervous system. Second major property, that this system produces very precise action. That means there is no amplification of the signal. If you decide to move one step, you move one step. You don't move 10 steps. Okay? Therefore, it involves very precise action. There is no amplification of the signal. This is opposite to what we will discuss about receptors which are linked to G protein. There is amplification of signal there, but here it is very precise action. There is no amplification of the signal. That means in one agonist can bind only one receptor. Once the agonist binds to the receptor, it can open or close only one channel or one ion channel. It cannot open 10. One agonist can open one channel. Therefore, the action is very precise. دقيق جدا. تقرر انك انت تمشي خطوه تمشي خطوه ما تمشيش 20 خطوه. Okay, just one a very precise action. This is the property of ion channel linked receptor, and they are used by the nervous system, and the action is very delicate and very precise. So, in summary, if we summarize what we have said before, we said that drugs act at different sites, including ion channels, membrane enzymes, membrane pumps, and receptors. Okay, we'll talk about each, inshallah, in future when we talk about groups, because drugs which act on the ion channels, there are groups, many different groups. So we'll talk about them in details when we talk about drug groups. A second summary we talked about, we said that receptors are generally they are protein structure, contain orthosteric and allosteric binding site. We said that the orthosteric agonist has affinity, intrinsic activity, and efficacy when it binds to the orthosteric binding site, while orthosteric antagonist, it has only affinity. It has no efficacy or intrinsic activity. We said that allosteric agonists increase the affinity and or efficacy of orthosteric agonists. We spoke about BAM and NAM. Last, we said that ion channels linked receptors, when they are activated by agonists, will lead change into membrane excitability, either towards more excitation or less excitation. And we have given examples of receptors which are produce nicotinic receptor and the GABAA receptor. We said that the ion channels linked receptor are used for fast nervous system activity. So by this we have finished our presentation today. Our next presentation, inshallah, which will be in a few days, we will talk about the receptors linked to membrane enzymes and the receptors linked to G protein. I have put some of the references that I have used for this presentation. You can look at it, and for any further information or further reading. I would like to thank you very much for your attention. If you like the presentation, don't forget to like it. Please subscribe to my channel, and please share the presentation if you can. I wish you a good day, happy life. Wassalamu alaikum wa rahmatullahi wa barakatuh.